The Ampere's law example with the coil sets us up really well now to talk about inductance. Which is defined as L, that being the inductance of the thing, is equal to this new variable called the flux linkage divided by the current. Now, flux linkage is not the same as just flux. It is the flux through all loops that are connected with the same current. So if there are, like there were in the coil example that we just did, if there are n loops of current I, and the same magnetic field lines go through all of them, then the total flux linkage, this is a capital lambda, by the way, is equal to the sum of all of the fluxes through each of the individual loops. So that's flux linkage, because those n loops of current are all linked by the same lines of magnetic flux here. We can use this to find the inductance of things, like inductors, but also other kinds of structures can have inductance too. In general, here's what you do. You use Ampere's current circuital law or the Biot-Savart law to find the magnetic field then you find the flux linkage, which usually you have to find the flux also. And you do that in terms of the current. And then lastly, you divide the flux linkage by the current. That's how you calculate the inductance of any old thing. So let's go back to that n-turn coil example. How do we do that one? It looks like an inductor. It's got to have some inductance. How do we do it? First of all, the magnetic field is uniform inside that coil. And we already found what it is. It is A hat Z and I over L. And I'll draw it over here in case you don't remember that one. It was, I'm drawing it as a cylinder, but it's actually many loops of wire wrapped around this cylinder. It has height L. The Z direction is up. And it has N loops, or turns. And it has current I. And because we know that the magnetic field is A hat Z and I over L, we also know that the magnetic flux density is mu naught A hat Z and I over L. So far, so good. The flux for one cross section since H is uniform inside, is just going to be the magnetic flux density times the area. So, I can write it out in integral form. It's the integral from rho equals 0 to A, if A is the radius, phi equals 0 to 2 pi mu naught Ni over L A hat Z dot ds, right? So ds is normal to the surface. The surface is a cross-section of this thing because the lines of magnetic flux are going up and down it like that. So ds is A hat Z rho d phi. And that works out to a total flux of pi a squared mu naught n I over L. That is the flux through one cross-section. But there are n loops that are all linked by the same magnetic flux lines. Remember, magnetic flux is solenoidal. It never terminates. It only makes loops. And if your loop goes around those loops, like really this situation kind of looks like this. And if your current loops are wrapping around these magnetic loops, then they count for this inductance purpose. So that means that the flux linkage is n times the flux from one loop because we have n loops. So that makes it pi a squared n squared mu naught I over L. Lastly, we need to divide by the current in order to get the inductance. So L is that over I, which is that over I, which is this if we just erase the I. And that's the inductance of an n-turn inductor wound on air because that is the magnetic permeability of air.